Now we'd like to use what we've learned about phasor domain analysis to analyze the circuit where we have the sinusoidal voltage source driving an inductor in series with a resistor, and we'd like to find the current flowing through the inductor. Our first step is to transform our circuit into the phasor domain. In the phasor domain, we'll still have a sinusoidal source. The symbol for a resistor in the phasor domain is the same as the symbol for a regular resistor, and the symbol for an inductor is the same symbol that we had for the inductor before. Now our voltage source will be expressed as a magnitude Vm at an angle, where the angle is the phase of the original voltage source, or 0 degrees. Resistors in the phasor domain are simply equal to resistors in the time domain, while inductors become j omega times L. Now we'd like to find the phasor current, which will have a magnitude and an angle. To analyze this circuit, we know that Kirchhoff's voltage law applies, and so the voltage across the inductor, VL, plus the voltage across the resistor, VR, minus the voltage across the source must add to 0, or VL plus VR minus Vm at angle 0 must add to 0. We can replace the voltages by the impedance multiplied by our unknown current, or we can write that the impedance across the inductor times the current through it, I at angle I, plus the impedance of the resistor, ZR, times I at angle I, must be equal to the applied voltage source at angle 0. I can rewrite the equation as ZR plus ZL, all times the current, I at angle I, will be equal to our applied voltage Vm at 0 degrees. And now you can see that I can solve immediately for the current I at the unknown angle will be equal to our voltage divided by the sum of these two impedances, ZR plus ZL. At this point we can replace R. ZR will be equal to R, and we know that ZL is j omega L. We can now make these substitutions and continue with the analysis. Now we can see that our current Im will be equal to Vm at angle 0 divided by R plus j omega L. For those of you familiar with complex numbers, you'll probably be able to move ahead to the solution, but for the rest of us, recall that in the complex plane, where I have a real part and an imaginary part, if I have some distance a and some height b, remember imaginary is equal to the j part, then if I express a vector as a plus b, which is a rectangular form, I can also express it in a polar form, where I'll have a magnitude of a plus b, and I'll have an angle, and the magnitude of a plus b, you'll recall from Pythagoras, is simply the square root of a squared plus b squared. Notice it's the real part squared plus the magnitude of the imaginary part squared. The j just indicates that it's orthogonal to the direction of the a. And the angle is given by the inverse tan to the minus 1 of the imaginary part divided by the real part. Using what we know there then, we can rewrite this as Vm at angle 0, that hasn't changed, divided now by the square root of R squared plus omega squared L squared at an angle of tan to the minus 1 of WL over R. Now I can find the magnitude as Vm divided by the square root of R squared plus W squared L squared, all at an angle. And remember, when I divide by angles, If these are in polar form, they'll be exponentials, so I simply subtract the exponentials or the angles, and I get minus tan to the minus